Or the next one is solid sodium amide is mixed with water. Amide is one of the IPE endings that aren't monatomic. Amide is a special ion. The reason why you should know amide is because it's
NH2, right?
It's NH2, and the reason you should know it is it's because it's a not just a base, but a strong base. And so sodium is Na plus, amide is NH2 minus, and sodium amide is NaNH2. NaNH2 is a very powerful base. This is a solid. Is it soluble in water?
Yes.
Yeah, all sodium salts are soluble in water. And what type of structure is this? Lattice? Lattice. So what would happen is it'd break apart in water to form sodium ions and amide. And so we could say, or because there's water present here, or we could say sodium ions and amide ions. That's what we expect because it's soluble. Sodium salts are soluble. So even though I wrote solid there, sodium salts are soluble, and we expect the lattice to be broken apart by the water molecules. And then we have water. And so if I look at this, is this a metathesis reaction? No, this is not a metathesis reaction. Okay, if it's not metathesis, then what? Well, it's got to be acid-base or redox. You have a feeling it's going to be redox? Well, let's first try acid-base. All we need is one. I'm not going to, there are ones that have multiple reactions. All we need is one, so let's try acid-base first. Sodium ions are amide. Amide is a base. Let me put up the chart again. Amide's a very powerful base. Here. Between this one, oxide and sulfide. Sulfide's a good base too. Sulfide is more powerful than hydroxide. Amide is more powerful than both of them. Oxide. And so it's a base. Pretty strong base. Water. Yeah, acid base. So the strongest base, amide or water? Amide. The strongest acid? Well, there's only one acid present, so it's got to be water. And so the reaction is going to be the acid water in the base amide. And this is my acid, my base. And so what forms? OH minus and ammonia. Okay, normally when we think of both of these as bases, you know, hydroxide is a strong base, ammonia is a weak base, but in this reaction, we got to label it going backwards. Going backwards, which one acts as the base, which one acts as the acid? So this is the base, and then this would be the acid. So it's a bit unusual, but it can happen. All right, now let's compare. Which one is a stronger base, or which one's a stronger acid? Let's look at the acids. Water or ammonia? Which one's a stronger acid? Water or ammonia?
Water.
Water is a stronger acid. This is weaker. That means the bases must fall. Amide's got to be a stronger base than hydroxide, and that's correct. And so we have driving force here. So we expect it to. In fact, do you know what the strongest base that can exist in water is? Hydroxide is the strongest base that can exist in water. All these bases are too strong to exist in water because all of these bases will attack water to form hydroxide. And so when a base is too strong to exist in water, the base attacks water and forms hydroxide, the strongest base that can exist.
Wait, what did you say when the base is too strong to form?
All those bases are too strong to exist in water. They'll immediately react with water to form hydroxide. So that's one of the reasons I wrote solid sodium amide. There's no such thing as aqueous sodium amide. There's no such thing as aqueous sodium amide because amide is too powerful of a base to exist in water. And so we could have amide here, but it's not going to last very long because immediately it's going to react with the water to form hydroxide. Hydroxide, strongest base that can exist in water. This is why, do you see the dividing line here? This is showing these bases don't exist in water. The strongest would be hydroxide. They're all too powerful. And so it turns out, wait, we got a reaction here. We don't have to go to redox. We got a reaction here. What makes a strong acid a strong acid? We look at the structure and the composition. But you know, these slides are made for Chem 1A, so skip this. Skip this. Lewis acid base, skip it for now. Identifying Lewis acid bases, skip for now.
So just skip Lewis acid.
Lewis acids and bases, we need to at least, at the bare minimum, come up with something called the Lewis structure. Lewis structure is arrangement of the atoms in there. We haven't even gotten this structure yet, so I'm going to skip all this other stuff. We're just doing Bronsted for right now.
Okay.
We'll come back to Lewis later. All right, I'm not going to talk about redox just yet. Before I get there, I want to talk about the inventory. Talk about the CE, the IE, and the NIE. This has to do with electrolyte, solubility and electrolyte. Well, essentially what we want are the major species. We're going to come back to it. We're going to what we're going to do is we're going to revisit some of these reactions. In fact, let's take a look at chapter 9. Homework right now. Okay, let's get some practice naming these things here. So this is from chapter 9, number 29. How would you name this one here?
Lead, nitrate.
Good. This one?
Potassium iodide.
Good. Well, what kind of reaction does that look like?
Metathesis.
Metathesis. This looks like metathesis reaction. What do we get here? So let's go ahead and do this. Actually, maybe we already did this one. These ones look familiar. But if we take PbNO32 plus Ki, I'm going to, you know the AQ? I get tired of writing that all the time, so I'm just going to leave off the AQ. But if you do the same, then you have to write solid, liquid, and gas. And if you leave off AQ, you have to leave it off for everything. You can't just say, okay, half of them I'm going to do, the other half I'm not, because I'm just a little tired, you know. You're going to have to be consistent. And so what does this form?
What?
What does this form?
Potassium nitrate
Uh-huh.
and lead iodide.
Yeah, lead 2 iodide and PbI2 and KNO3.
3.
Okay, is there a driving force?
Nitrate.
Nitrate salts are all soluble, potassium salts are all soluble. That's not going to drive anything. How about this? Iodides are all soluble except for silver, lead.
And mercury.
And so we have a driving force. The driving force we call PBT. And therefore we're going to balance it. How do I balance this?
Oh, hold on. 2 NO3s.
2 NO3s here, so I need 2 NO3s here.
And then 2 potassiums on the
Yeah, then that's balanced. Okay, this is what we call a CE. And then we have something called an IE. An IE is going to list all the species present in solution. And so if I have, this is in water because this is AQ. If I have lead 2 nitrate, will the water break apart the lattice? Lead 2 nitrate?
Yes.
Yeah, it's a soluble salt. Soluble salt, the water is going to come in here and break it apart into what? And so we separate it ion by ion. We're going to get lead 2 ions and nitrate ions. And to keep everything balanced, I'm going to write 2 nitrates. So for every lead that gets torn off the lattice, 2 nitrates will 2.
What does CE stand for again?
CE stands for the complete
Complete.
equation.
Oh.
This, what we're generating now is the ionic equation, or the IE. How about potassium iodide? That's a soluble salt. Soluble salts get broken apart, right, into the ions, and the ions would be potassium ions and iodide ions. But I don't want to screw up the balance. We just balance this. So I don't want to screw up the balance, so I'm going to write 2 potassium ions and 2 iodide ions for every 2 KIs that get broken apart. Okay, that's soluble salts. What about insoluble salts? Do insoluble salts get torn apart by water?
No.
No, insoluble salts do not. And so this is just going to stay as is. The water doesn't break it apart and dissolve it, otherwise we'd have to call it soluble. This is insoluble. And then how about KNO3? That's aqueous, so that's going to be broken up into 2 potassiums and 2 nitrates. And so this is the way we visualize this. The way we visualize this is if I had a beaker that's labeled lead 2 nitrate, what am I going to find inside that beaker? I'm not going to find crystals. Am I going to find crystals with lead 2 nitrate? No, instead I'm going to find ions, lead 2 ions and nitrate ions. And then I have a separate beaker. In a separate beaker, I'm going to put in, yeah, this is going to be labeled Ki. And I'm not going to find crystals of Ki. Instead, I'm going to find potassium ions and iodide ions. Now what I'm going to do is I'm going to take these 2 beakers and mix them together. And so if I combine the 2 beakers, I'm going to get my reaction mixture. And so let's go ahead and combine beaker to get my reaction mixture. The reaction mixture is going to consist of lead ions and nitrate ions and potassium ions and iodide ions. And then what I do is, what are metathesis reactions? Metathesis reactions are favorable.
2 ions.
It doesn't have to be 2. Favorable ion combinations, right? That's what it is. It's favorable ion combinations. Favorable ion combinations, oh, do you see a favorable ion combination?
Yeah.
I see it. Lead likes iodide. Lead and nitrate, no, it's not favorable, otherwise they'd come together and precipitate. You know, water keeps them separate. If I evaporate the water, yes, I can get lead 2 nitrate back, but I have to evaporate all the water. And so what's going to happen is the lead ions and the iodide ions are going to come together to form a, yeah, and this lead iodide is going to form a solid on the bottom. Well, it's probably going to be cloudy, and eventually it'll form a solid on the bottom, which is PbI2 solid. Okay, but what about the potassium and the nitrates? Are those going to come together to precipitate? No, the potassiums and the nitrates stay in solution. So essentially, really nothing happens to the potassium and nitrates. You see the nitrates are in solution before, and then after the reaction, the nitrates are still in solution. And so what we call the nitrate is, we call it a spectator because nothing happens. We have nitrate aqueous, we have nitrate aqueous. Also the potassium ions, nothing happens to those. Those are spectators as well. So those are spectators. And so if we just look at the ion combination that looks good, the ion combination that looks good is this. It's lead ions, like the 2 iodide ions, to form lead 2 iodide solid. In other words, we eliminate the spectators. If we eliminate the spectators, then we're just looking at the ion combination, the favorable ion combination here. And this is called the net ionic equation. The net ionic equation. Or the NIE. Net ionic equation. So that's what, in this homework assignment, they just want the net ionic equation. But in order to get the net ionic equation, what we had to do is we had to go through all the equations. And so on the test, I'm going to ask you to write things like the CE, the IE, and the NIE, net ionic equation. In the homework, they had you skip. All right, number 30. Let's take a look at number 30. If you look at number 30, what kind of reaction does that look like? Yeah, that looks like metathesis to me. And so what forms? Well, let's name these. Let's get some practice naming. Well, actually, let's name these. This is called lead 2 ion. Yeah, lead 2 iodide. Lead 2 iodide, tell me how I should spell it. Should I spell it like this? Lead space 2 iodide? Yeah, there's no space. It should just be lead, Roman numeral 2, all one word, iodide. So it's 2 words. Lead 2 iodide. This one is called cobalt nitrate.
Cobalt 2 nitrate.
This is called cobalt 2 nitrate. This one's called potassium phosphate. Yeah. Potassium, is that with 1 S or 2 S's?
2 S's.
Yeah, 2 S's. So we take cobalt 2 nitrate and potassium phosphate. What are we going to form? We're going to form cobalt 2 phosphate and potassium nitrate. So let's go ahead and do that here. So cobalt 2 nitrate plus potassium phosphate. Okay, give me the formulas. What is cobalt 2 phosphate's formula? Well, that one's tricky, so maybe I'll write it up here. Cobalt phosphate. How many cobalts will I need? 3. And how many phosphates? Is that solid, liquid, gas, or AQ? All phosphates are insoluble except for group 1 and ammonium. Group 1 and ammonium. So cobalt's not an exception, so this is actually solid. It's insoluble. Plus potassium, which is this KNO3. Is that soluble?
Yes.
Yeah. Is there a driving force? Yeah, the driving force for this is precipitate here. All right. Since the driving force would balance it, so how many cobalt 2 nitrates do we need?
3 cobalt.
How many potassium phosphate? And then how many KNO3?
6.
Okay, no. Okay, we call this the CE. Let's do the IE. In the IE, is water going to break apart the lattice? And the question is, will water break apart the lattice? Yes, if it's a soluble salt. No, if it's an insoluble salt. And so water will break apart the lattice for soluble salt. Is this a soluble salt?
Yeah.
Yeah. And so what is going to form? Well, we're going to break it apart into ions.
Yes.
How many cobalt ions?
3.
3 cobalt 2s. How many nitrates?
3.
No.
What? Oh, 2. 6.
No. 6.
My bad.
6 nitrates.
Sorry.
Okay. Will water break apart this potassium phosphate? Yeah, it's a soluble salt. That's what's going to happen. Water is going to tear apart the crystal lattice, and it's going to form how many potassiums?
6 potassium.
6 potassiums, and how many phosphates?
2 phosphate.
2 phosphates. Good. Will water break apart the cobalt 2 phosphate? No. So this is just going to stay. The lattice is too strong. It's going to stay together, right? The lattice is too strong. It stays together as a salt. How about KNO3? Will water break apart that?
Yeah.
Yeah. And what's going to form?
6 potassium ions and then 6 nitrates.
And 6 nitrate. Okay, then we look. What didn't change?
The cobalt.
The cobalt did change because it went from. The potassiums didn't change. You see, after 6 potassium ions here, 6 potassium ions here, nothing happened to it. And then what else didn't change? The nitrate. The cobalts did because they precipitated. And so the nitrate. So the favorable ion combination here is just the 3 cobalt 2s plus 2 phosphate ions yields CO3 PO4 2 solid. So that's a metathesis reaction, which is the favorable ion combination. Okay, I guess we'll stop here and then we'll continue next time.